In this lecture, we are going to look at optical lithography, in particular surface reflection. So far we looked at image formation, how a light beam comes onto the wafer surface and interferes with the other beam. So we had zeroth order and +1 or -1, and then you get a intensity pattern on the wafer. So now the question is, what happens in the resist, and also the interface between the resist and the substrate, and the interface between resist and air. So these reflections that occur between these interfaces could result in undesirable image formation. So let's look at what are all the undesirable process that happens, and also how we try to solve these reflection issues. So when you take a substrate and coat it with photoresist here, and then you illuminate, and then we create a trench. Okay, so this is a very simple process, and this is achieved by illuminating it, let's say through a mask, right? It could be contact mask, or proximity, or this could be projection. So in all three cases, you have light beam coming onto the photoresist. So on the right side image, we see a ray model of different transmission and reflection. So this is an example of a ray that is coming in, going through the photoresist, and this is what this is the photoresist, and you're trying to expose the photoresist through this beam. You will have also reflections from here because there is a difference in the refractive index, right? So this is very fundamental. Whenever there is a refractive index or density change, light will reflect and refract. So in this case, light is reflected from the top interface. Let's say this is air, and then we have refracted beam, and then you have another interface. Because we have a difference in refractive index between photoresist and substrate, you will have reflection here, and then there is again a refraction, and then there is a reflection, and this goes on, right? So this is just a exaggerated image of the ray model, but ideally if you look at orthogonal beam, so you will have beam bouncing back and forth with the normal incidence, right? So this is just to show what are all the possible reflection paths, right? Just to give you an example, the difference in the refractive index, right? The refractive index of air is 1, and photoresist, that could be something like 1.8, let's say, and refractive index of let's say if this is a silicon substrate, this could be 4, let's say. Okay, so this is how your refractive index contrast is going to look like. Because there is an inherent difference in the stack, you will have this reflection, right? So ideally you want only a single beam, and then it should expose the photoresist. But now we have beams that are trying to bounce back and forth, and this bouncing back and forth could result in undesirable exposure. So this could expose portion of the resist that should not be exposed, that is not designed, and also this could create a standing wave. Because you create a cavity like structure here, it can bounce back and forth and create a standing wave, right? Let's see how these things affect and how we solve this problem. On the left hand side, we have a simple photoresist, right, coated substrate, and on the right side we have something coated on the resist. Let's first analyze what is on the left side, right? So we have two beams. One is the refracted beam that is coming in, and also the other one is the reflected beam, but this is within the photoresist, and these two beams, they have same direction, right? So in principle they will interfere with each other. So if these two beams don't have any phase difference, right. So, these are all the two beams, and if they add or interfere with each other, it will create a standing wave. So, this is the standing wave we are talking about, right. So, the intensity of light within this photoresist region will look something like this, okay, because there is no phase difference, right, between these two beams. But this intensity variation within the photoresist is something undesirable, because ideally you want a flat exposure, right. Uniform intensity of exposure is what you are trying to achieve, but in this case you have intensity variation along the thickness of the photoresist, which is something you do not want. But let us look at how we can avoid this. The primary reason why we get this standing wave is lack of phase difference between the two beams, here the orange and red beam, right. So, there is no phase difference at all. So, if you want to cancel it out, what we can do is, this orange beam is the first incident, so right, we can't do much about it, but then when the light is reflected back, and then there is an internal reflection that happens, right. So, there is a reflection from here, and also there is one more reflection because of this coating that we have. Let us call this layer anti-reflective coating, okay. So, this is just an anti-reflective coating or any polymer material that we coat on top of this, that also reflects, right. So, you create another interface that reflects. So, now the primary idea is to create a phase difference between this beam 1 and beam 2. These are all the primary beams, right. The reflection from this edge, right, you may ask what is happening to this edge, right. So, we reduce the reflection here, we do not want much reflection to come here, and that is designed by the refractive index contrast between the anti-reflective coating and the photoresist that we have. We will look at what is the rule that one need to use in order to get this refractive index matching, but for understanding this interference, let us only look at this beam 1 and beam 2. So, now beam 1 has the same phase, but beam 2 has acquired opposite phase. If you look at the phase here, they are completely opposite phase, right, and this is achieved by adding this layer. So, this layer acts as a phase shifter now, okay. So, this will give a pi phase shift to the reflected beam, and when these two beams B1 and B2 interfere, it will create a destructive interference, right. So, this if you look at this as the intensity axis, you are going to have 0 power going through. So, you are trying to arrest whatever reflection that we have, and the exposure is only due to the incident light, right. So, in this case you will have a uniform exposure and not standing wave type exposure, and this is the result of such a anti-reflective coating. On the right side you see a coating, right, a photoresist coating without anti-reflective coating, and here because of the reflection you have this standing waves on left and right side, right, and then you create this wavy pattern, right. So, it is not a smooth sidewall anymore, it has a wavy pattern, which is something that you do not want, because you want the sidewalls to be smooth, because whatever roughness you have on the photoresist is going to be transferred to the underlying silicon. So, you want to make sure your photoresist sidewalls are smooth, okay. On the left hand side you see the photoresist profile with very smooth sidewall, and here this is with anti-reflective coating. When you use anti-reflective coating, you arrest the reflection and you make a uniform intensity exposure in the photoresist, okay. So, this is how you can reduce the standing wave pattern in the photoresist and achieve a smooth sidewall, right. And if you look at some real images, this is how it would look like. This is a scanning electron microscope image of a photoresist after development, and you can see the wavy pattern here, right. So, you can look at the pattern here, which is clear that there is a standing wave created because the anti-reflective coating was not there. Okay. And if you are going to use this for dry etching, you are going to transfer the non-uniformity that you have on this photoresist onto your silicon or underlying pattern. Okay. So, you have to be really careful about this reflection, right, that you get from the substrate to avoid this. And how do we choose this anti-reflective layer, right? I mentioned that this layer could be polymer, right. So, it should be polymer, and we should be able to coat this layer, right, using spin coater. So, you can either use it on top or at the bottom, right. In this case, it is TARC, which is top anti-reflective coating. If you put it at the bottom, it becomes bottom anti-reflective coating. So, you can have a silicon substrate, and then you will have bark, right, bottom anti-reflective coating, and then you can have photoresist. So, here again the mechanism is the same. So, you will have light coming in, and then we have reflection from here, and then we will have reflection from here, right. So, you can arrest the further reflections by creating a pi phase difference between the reflected beam of the photoresist and the reflected beam from bark, right. So, this is how you create the phase difference and avoid the standing wave pattern. Okay. So, TARC and bark is what you can use, and what is the refractive index and what should be the thickness is a very important point here, because the phase shift depends on the refractive index and the thickness, the optical path length the wave is going to take, right. So, the refractive index to a large extent you can choose with this following relation, right. So, you know the photoresist that you are going to use and the refractive index of the photoresist, and then the square of that should be your refractive index of the coating layer, in this case top anti-reflective coating layer, and this should closely match your requirement for back reflection arrest, right. And what should be the thickness? Thickness should be lambda over 4, right, which is very typical. So, here it should be lambda over 4n. The reason for this is the the wavelength that you are going to use is going to be inside the anti-reflective coating layer, right. So, the wavelength of light inside the medium is nothing but free space wavelengths to the refractive index of the medium. Okay. So, for instance, if lambda naught is the free space wavelength, so if I am putting this light through a medium, let us say it is glass, right. So, it is going through glass, and this is lambda naught, right, which is in air. And now, if it goes through glass, the wavelength is not lambda naught, the wavelength inside glass is lambda naught over n glass, right, refractive index of glass. So, in this case it could be lambda naught by let us say 1.45, right, approximately. So, this is actually the wavelength of light, right, so the path that it is going to take. So, lambda over 4n, right, where n is the refractive index of your anti-reflective coating layer. So, if you can choose the right kind of refractive index and the right thickness, we should be able to arrest any reflection. So, this will act as a anti-reflective coating either on top or at the bottom. So, if we do the coating, right, and then we go through the illumination process, and then we can do the development, and this is what you will get. In this case it is bark, this is bottom anti-reflective coating, this is cross section image of a substrate, right. This is a silicon on insulator substrate, and you had silicon dioxide, we coated with bark, and then we had photoresist coated, and then we illuminated it, right. So, you illuminate it with a light source, and that would create this particular pattern here, and then once you have a particular pattern, then you are going to develop this, right. So, when you develop this, your bark is still there underneath silicon and silicon dioxide on the top. So, you get this photoresist. Let us assume this is a positive photoresist and this is the illuminated part, right, and this is your photoresist, right. So, if you look at it, the bark layer is still there, right, the anti-reflective coating layer is still present. So, what is the next step we are going to do? Probably you are going to do this for dry etching, let us say, right. If you are going to do dry etching, you should open this bark layer in order to get access to silicon. Okay. So, you want to remove this bark layer before accessing silicon. So, normally a bark breakthrough, right, a bark removal step is applied before doing silicon etch. This can be done in one sequence, you don't need a special step, this is part of the silicon etch process itself, right. So, the problem here is this bark layer is insoluble in photoresist, right, in photoresist developer. Okay. So, the talc in some cases is soluble in water or in the developer, right. So, that makes life much easier, right. I am going to draw how the talc is going to look. So, this is photoresist and this is talc, right. This is top anti-reflective coating, and when you expose this material, right. So, in this case again, let us say it is positive resist, you are exposing it, your top anti-reflective coating layer should also be transparent to your illuminating wavelength, which is again a very crucial requirement. It could be anti-reflective, but at the same time it should not have absorption, right, large absorption, right. So, if it has absorption, then the amount of light going into photoresist is going to be lower. So, you need a larger dose, right, in order to illuminating dose in order to get the photoresist exposed. So, in this case the top anti-reflective coating should be transparent, and once it is exposed, you will get this exposed part. But now if the top anti-reflective coating is insoluble, then you won't have access through the top anti-reflective coating to develop this exposed part, right. So, this is the exposed part. So, you want to remove this exposed part, right. So, this is where the exposed part is, and you want to remove this exposed part, right. So, unless you remove the top anti-reflective coating layer, you won't have access to the underlying photoresist, and that is one of the reasons why your top anti-reflective coating is soluble in the developer, right. So, when you are putting into the developer, your whole top anti-reflective coating will go off, right, including the one on top of the photoresist, because you do not need it after exposure, right. So, when you develop it, you will get something like this. You will only see photoresist, your top anti-reflective coating will be gone. Okay, and this is what you will get after development. And another important thing to notice while using anti-reflective coating is what is the subsequent process that you are going to use. For instance, if dry etching is your subsequent process, you can use bark etch as one of the steps to remove bottom anti-reflective coating, and in case of top arc, you do not have any issue, right. But then if you are going to do lift off process, let us say, right. So, I am doing this lithography process in order to do lift off, right, for metal deposition and so on. In that instance, having bark layer could be an issue. So, you may have to go to a bark removal step separately and then come back for material deposition. Okay. So, keep in mind what is the subsequent process and whether you need silicon access or not, right. So, based on that you may have to apply a separate bark removal process in order to get access to silicon if you are doing material deposition, or in case of implantation also, right. So, if you are doing implantation where you want to expose silicon, you may also want to remove bark, right. So, bark layer will reduce the energy of the implant ions, right. So, you want to remove bark layer when you go for implantation. Okay. So, these are all the various considerations you should have while using this bottom anti-reflective coating. And another important thing to understand is swing curve, right. So, swing curve is nothing but variation in critical dimension with respect to resist thickness, right. If there is a thickness variation, your resist line width will change. Okay. So, the reason for this is twofold. One is your amount of energy that you have, and also your reflection. Okay. So, we looked at the photoresist thickness, and then we saw this standing wave, right. So, the standing wave pattern would result in a certain CD or certain dimension, and based on the thickness of your photoresist, the standing wave wavelength or pitch will also change. Okay. And this change in the standing wave pattern will result in varying thickness or varying critical dimension with respect to thickness. You can see here when the thickness increases, there is no monotonous increase in resist line width, right. So, for various bark thicknesses, you see there is a swing, right. But then you should also notice that at an optimal thickness, in this case 80 nanometer, right, 80 nanometer of bark, you see the swing is almost null, right. You do see a very small swing, but it is very minimal, right. With thickness variation, you see a very small change in the critical dimension. Okay. And you want to reduce this swing. The reason for that is you will always have some resist thickness variation, right. When you are coating a 200 millimeter wafer or 4-inch wafer, or 300 millimeter wafer, there will be some change in the thickness as you go from center to the edge, right. And this thickness variation should not affect your line width across the wafer. Okay. So, you want to make sure that your resist thickness variation will not affect your critical dimension variation. And here bottom anti-reflective coating is helping you to solve that problem, right, because the standing wave that you get is almost arrested completely, right. And that is what we see on the right side map, right. So, on the x axis bottom and top you have bark thickness, on the left side you have left and right you have the resist thickness variation. The color shows the line width. Okay. So, if I take a suboptimal bark thickness, right, if you remember the bark thickness, right, for optimal bark thickness you need right refractive index and right thickness, right. So, both are important. So, assume that I took the right refractive index, but not the correct thickness, you will still have reflection, and that is what we capture in this map, right. If I take 50 nanometer thick layer, or rather let us say 60 nanometer, because on the left side we have a line scan of that, right. So, if I go along this length, what I see is the swing, right. The CD is varying with respect to resist thickness. That is what we see on this left. So, left side is the line scan of this, but if you look at 80 nanometer, you almost see no change for a very large range of photoresist thicknesses. Okay. So, this is the thickness that you want to use to have optimal CD uniformity for resist thickness variation as well. So, you will choose a particular thickness of bark for the particular thickness of resist, so that your CD variation is minimal, right. So what are these variation? What kind of thickness variation in resist and what kind of thickness variation in bark one can expect, right. So this is just a a sample data. You want to improve or to maintain a very high uniformity of thickness of photoresist and anti-reflective coating, but it is technologically limited, right. So what I am showing you here is a photoresist thickness variation over a 200 millimeter wafer, and this is bark thickness variation over a 200 millimeter wafer. But if you look at the range, right, so here the range is about 5 nanometer, and in this case the range is about 1 nanometer, right. So the thickness variation over a 200 nanometer or 200 millimeter wafer can be less than 5 nanometer. This is achievable with current technology. So when you are designing your process, you may want to make sure that your anti-reflective coating thickness, right, is able to match the photoresist thickness variation you are going to get. So you work towards achieving the maximum uniformity for photoresist. At the same time, you need to choose the optimal anti-reflective coating thickness in order to achieve uniform critical dimension over the wafer. Okay. So with this we come to an end of this reflection problem, right. So how the reflection is affecting your critical dimension, and also not just the reflection from the surface and interfaces, but also the thickness variation. So if the resist thickness varies, how the anti-reflective coating layer could be used to mitigate this issue. So by using the right kind of anti-reflective coating and the right thickness of anti-reflective coating, you should be able to achieve uniformity in your critical dimension over the wafer, even though you have a slight variation in photoresist thickness, right. So this is all towards achieving a better uniformity, better yield by adding this anti-reflective coating. Sometimes it might be an additional process, but you get a yield improvement and the uniformity by doing this additional step in achieving a better process in lithography.